Once you have a sketch, compare it to someone next to you. See how your sketch compares. So given this rate function, what, just in general, what's one characteristic of the accumulation function? What could you say? That it's going to do what? Always. Always going to increase, right? Because our rate is positive. Okay, so we've learned something. This is good. So somehow the graph is going up. Now, what does it mean that the rate kind of gets big around 5 to 15 minutes? It's larger, and then decreases again. What will that mean for the accumulation graph? Yeah, so you got the right idea. It's going to be heading up more sharply, right? The volume will head up more sharply when the rate is higher, and it'll only head up gradually when the rate is lower. This is old stuff. So let's take a look at that. So something like this. Okay, so we've been down that road, and we've dissected it. But what if we wanted to know I don't remember which it is, sorry. If we wanted to know what the rate was given a number of the volume poured. So what if we were interested in what the rate was now, not as a function of time, but as a function of the volume poured. So that's a different question that's kind of not answered by the kind of the accumulation from rates process that we've worked on in the past. Okay? So what could we do to come up with that relationship? Just say maybe graphically. So any suggestions? How could we come up with a relationship now of given amount poured, the corresponding rate for that amount poured? What could we do? Yeah. So like a composition? So yeah, so say we just want to come up, we get just a rough sketch of that relationship. So not so much that we want to know what the formula is, but just a rough sketch of the relationship. How do we know, say, what the rate of change is at 10 meters cubed? So here's 10 meters cubed. There was some rate when the amount poured was 10 meters cubed. The concrete was pouring at some rate, and that would be a point on our graph. So how could we determine what that is? You've got all the information you need, right? So what would that look like? Yeah.
We have the value of like accumulation on the right there in blue.
Okay.
So you can take like the slope using like an infinitesimal like dx, get the slope at that point. Like that's like tangent to the curve. So you can graph those slopes and the amount of accumulation. So you can have like, if you have like a slope at 10, you can use that slope and 10 to create a new point on that graph.
But what is, so you're talking about the slope of 10 here?
That's 10 minutes, not the slope
Right.
of the y is related to the y.
Okay. So over which one? Oh, sorry. Let's say like what did I say? Meters cubed poured. So let's say like 200 meters cubed. Sorry. Let's make it easier here. 200. 10 was not enough. So how could we identify that point? At 200 meters cubed, what's the rate of concrete being poured? Any ideas? What do you know about 200 when 200 meters cubed is poured? What do you know? Yeah, begin.
So on the right graph, you have meters cubed.
Right.
So if you find 200 on there.
Right. Is that down the x-axis or the y-axis?
And then you use that minute to go back to the left graph to find meters cubed over minute.
So where do I see meters cubed on this graph? Where am I going to look to see meters cubed, 200 meters cubed on this graph?
200 meters cubed matches to 200 meters cubed. So like.
Just.
Go to like.
Okay, so that's the y-axis, right? The
Yeah.
y-axis. 200 meters cubed on the y-axis, and so.
And then like match it and then find the minute for that.
Uh huh.
And then you mark that minute, remember what that boy is, and then you go back to the left graph.
So about 7 minutes.
Yeah. And then
Okay.
go back to where 7 minutes is here, and then go up and match that to that.
And that gives us this point gives us the rate. The y-coordinate gives us the rate. So the rate is about maybe 72 or something. So what's the go between here? Minutes. So when we draw that graph, what minutes is going to be gone, right? Minutes is going to be gone out of that graph, but it's kind of the key quantity behind the scenes, right? It's the key quantity behind the scenes in constructing this graph of meters cubed per minute, because it's minutes that allows us to bridge the gap between meters cubed and meters cubed per minute. Does that make sense? Okay, so rather than think about, okay, given a meters cubed, what's the meters cubed per minute? Let's instead start with numbers of minutes, right? So given a number of minutes, I can easily find what? Both, right? So given a number of minutes, I can find the rate, and I can find the volume accumulated, and that will be a correspondence point on our new graph, right? So let's watch this in action here. Yeah. So here we go. Okay, so for t equals 5, so t equals 5, we're going to have t equals 5 for both graphs, the corresponding rate on the left, and we're going to take, it's a little faster than I can talk. But did you see what happened? I'll do it this way. Here we go. So for t equals 5, you're going to have to do this. So if just watching isn't, it's not going to stick, then you need to take notes. So start with t equals 5. I can get, with t equals 5, over there on the left, I can get the y-coordinate is the corresponding rate of change for t equals 5. And then on the right, I can get the corresponding volume accumulated at t equals 5. And I'm going to take that volume, that y-coordinate, and make it our x-coordinate down below. That, and then the y-coordinate of the rate, I'm going to make it the y-coordinate because it's still rate is on the y-axis. And that gives us that correspondence point of volume and rate when, after 5 minutes. And then we can just keep doing that. So then the next one we can do is t equals 7. This is kind of the one we looked at. So for t equals 7, we get the rate on the left, we get the amount of concrete on the right, amount of concrete is x-coordinate, rate is y-coordinate, and and we get the correspondence point of the rate, and then et cetera. T equals 9, same thing. And again, it's the number of minutes that's in this new graph that we're making, this new relationship we're making. Number of minutes is this key quantity that doesn't get graphed, but it's definitely behind the scenes forming this relationship. That's the key. So this is the idea of what we call a parametric function. A parametric function, the independent thing is what we call the parameter. So the independent thing here is the number of minutes, even though that number of minutes doesn't get graphed. So then we can see that smoothly. So here's using a table and plotting a bunch of those. And then we can see kind of the overall graph take shape. And this makes sense. I mean, this kind of mirrors what we knew about the rate graph, that at the beginning, when there's not much volume poured, it's coming out slowly. And then when more volume has accumulated, now it's coming out faster. And at the end, when all the volume, most of the volume of concrete has accumulated, the rate is dropping. So to see that being generated smoothly, so this is if you were to do plot all those points like continuously. And this is that relationship that we were after. The rate of change now shown on the horizontal axis, but then volume shown on the, vertical axis, volume shown on the horizontal. So this is the idea of a parametric function. So before we define parameter, if you were in the Calc 1 course for the revised, like with myself or Jennifer Bonney, we defined a parameter as it stays constant in a given situation but can change from situation to situation. Remember, a variable changes in the given situation, and a parameter stays the same in the situation, but then if you change situations, the parameter can change. Well, now our different situations are like at different points in time, and now we can allow that parameter to vary through situations, right? In this case, situations meaning distinct points in time. So what we call a parameter now will vary to produce the parametric function. So now, t, the time since the pour started, in minutes, which was t, is called the parameter. And so being consistent with what we said before, again, we said a parameter would stay the same from situation to situation. Well, now what we think of as situations are different amounts of times since the pour started. And then we can think of those different situations, and then now we can vary t and let that parameter vary. So that in parametric functions, the parameter is a variable. Okay, so that to make our definitions make sense, right? So with these parametric functions, that parameter is actually varying. It's varying behind the scenes. You see, it's not graphed in what we wanted. It's not part of that graph, but it's this essential invisible element. Okay, so let's take a look in in GC, how can we do that? Can we graph parametric functions? Because you're going to be using GC for your homework. So this rate of change function was this right here. So let me copy that. Start a new file. So there's my rate of change function. And then to graph a parametric function, you're going to do control 2. Control 2. And so then each of x and y are a function of t. So x we wanted was, what were we showing on the x-axis? Rate of change or volume? Volume. So if this is the rate of change, how can I express the volume as my x coordinates? So I heard derivative and I heard integral. Which is it? Accumulation, right? Given rate, we want accumulation. That is integral. So I can do Control-Shift-I of r. Right? Why type that out when we can use function notation, right? R of yeah, so since I've defined a starting at 0, we could put that a in there, and then if we want to start at a different time, we could just change a. So yeah, so either a or 0 will work for this case, but to be generic, we can do a. All right, and then what about y? R of t, right? Okay, so what is this telling you to do? It's saying as your x on the horizontal axis, put the accumulation of r, the integral from a to x of capital R function, and on the y-axis, put just the r function itself. So when we graph this, so this is telling it to graph. X is a function of t, y is a function of t. Can't graph equations of this form. What am I doing wrong here? So let's actually define that integral function outside. So we'll say a it might not like the integral inside there. So let's do this. I just copied and pasted this. And now in here we want what? A of t. What's that? No, but so parametric functions are going to be functions of t. You need to use t. That's the point. You need to use t. So what we're going to do is, why is that not working? Look in the book. Here it shows us how to do it. What's that? Right, this needs to be x. There we go. Okay, so we just had, we needed our independent variable to be the top limit of integration. Okay, so now I think we got it. There we go. All right, so what happened? So if we were expecting this, this graph of the whole thing, right? And we just got this little teeny piece. So what happened was, if you notice, when you graph a parametric function like this, and you have to use t. Okay, so t is built into graphing calculator. Whenever you do the control 2 and do these stacked called vectors here, you have to use t to get a parametric function. That's what it knows. So we got to use t. But if you notice over here, what popped up? It's showing t from 0 to 1. Okay, well that's just showing in the first minute, and that's what we're getting. We're getting the first minute of this graph. So what did we have? How many minutes? 25 or 30 minutes, right? Okay, so if we go back there, and so we got two things we can do. The first thing we can do is just change t and say from 0 to 30. And that'll give us those values of those functions for all t values from 0 to 30. And then if I zoom out, that's the same picture we looked at before, right? Okay, but there's something that's a little more maybe strategic, and that is if we're graphing maybe more than one parametric function at once, we can't change these ranges of t for different parametric. So if I had maybe 2 or 3 more parametric functions, we've got to graph them all for the same range. So another thing we could do is keep t from 0 to 1, and then do what? How could we adjust our function now to show what we want it to show? So we want to show from a of 0 to a of 30 as t varies from 0 to 1. So t is varying from 0 to 1. And if we just, this argument we want, so argument is what goes into the function. We want the argument likewise to go from, not from 0 to 1, but from 0 to 30. So we can just think of a little covariational relationship there to redefine the argument from t to what? How can I change the argument so that as t varies from 0 to 1, the argument will vary from 0 to 30? 30t. So I can just come in here and do 30t. And this way, if I'm graphing more than one thing parametrically at once, we can just adjust all our functions so that they work for t equals 0 to 1. Okay, so let's see how we're doing this. So I think most of us got that we want to use his distance traveled along the highway, or distance from his starting point along the highway. But if you just quickly sketch those graphs, you really don't know what is equivalent in order to make the third graph. Okay, so what I suggest is, let's mark off some like mile markers. So maybe like pick a distance, and then we're going to relate those distances to each of the two introductory graphs, or the first two graphs, so that we're not pulling off a distance from Casa Grande and a distance from Maricopa at a different distance traveled, right? When you do this, you've got to pull off a distance from Casa Grande and a corresponding distance from Maricopa for the same distance traveled along the way. Does that make sense? And if you just sketch the graphs fast, you won't know where those match up. So we got to be a little more systematic about it. So if you can, so how many do I have? This may be a little too many. 1, 2. I got 11. All right, so I picked 11 kind of equally spaced points along the way. Then kind of you can gauge your distance from Casa Grande according to those, whatever, 11 distances, and same with your distance from Maricopa. So we want the best sketch we can of the final sketch at the bottom. So I noticed, so lots of you are leading off what's going on here off your graph. Okay, so make sure you have that aspect of what's happening actually all the way starting from here. Okay, so when you match up these points, I'll just give it a general kind of thing here. When you match them up correctly, so at first, what, farthest? Distance from Maricopa. It's the furthest, right? And closest, right? Closest to Casa Grande. Okay, and getting closer to both of them. And then we start getting further from Casa Grande, but closer to Maricopa. And then we come to that point where Jacob is closest to Maricopa. And what happens after that? Further from both, right? So that's that part I was highlighting here. Up here, getting further from Maricopa and further from Casa Grande means this is going to roll back to the right and go up. So my question is this the graph of a function? So it's a big point here. Is this the graph of a function?
No.
Is it the graph of a function? It is absolutely the graph of a function. Yes, it is. Is distance from Casa Grande a function of distance from Maricopa? Is distance from Casa Grande a function of distance from Maricopa? That's the question you thought I was asking. Is distance from Casa Grande a function of distance from Maricopa? No, because given a distance from Maricopa, there's more than one distance from Casa Grande at some distances from Maricopa. So when I asked that original question, is this the graph of a function, many of you answered as if I was asking, is distance from Casa Grande a function of distance from Maricopa? And the answer is no. But it is the graph of a function. What kind of function? A parametric function. Our independent, so we can say our independent quantity is what? Distance driven from the starting point. It's not a part of the graph. It's not driven on here, but it's our parameter, right? The independent is our parameter, distance driven. Or distance from starting point. What's the dependent thing? Unordered pair, right? So the independent is this parameter. It's this behind the scenes variable, the variation of distance from starting point. And then the dependent thing is now an ordered pair, not just one value, but an ordered pair. And so can you say, given any distance driven, is there only one correspondence point of distance from Maricopa and distance from Casa Grande? Yes. So given any distance driven, it gives us just one correspondence point on this graph. That's why parametrically it is a function. So the dependent is an ordered as a correspondence point for any given distance driven along the highway. So that's the idea of a parametric function.